guys. In this video, we're going to go over the kinetic theory model. So we're going to go over how to derive it because all exam boards need to know how to derive it. The only slight difference is that in AQA, they represent root mean square speed by writing actually root mean square speed. So that's what RMS stands for. So you can see it here, root mean square speed. So R for root, M for mean, S for square speed. But in OCRA, instead of writing CRMS squared, they use a C with a little line above it to represent that root mean square speed. Root mean square speed. So you see, it's that same thing. It's still C squared, but here they use a little line on top in OCRA to represent root mean square speed, whereas in AQA, they actually write RMS. So AQA normally aren't that nice to you, right? Normally it's harder than the other papers, but they're actually really nice to you here because they actually write RMS to remind you that's what it means, root mean square speed. Another nice thing that AQA does that OCRA doesn't do is they actually write the words kinetic energy of a gas molecule equals this equation, okay? In OCRA, you just have the equation, but again, instead of CRMS, you write C with a little line above it. But you just need to remember, because that little m stands for mass, so again, that little m always stands for mass of a particle or of a molecule. That's why you know this equation is used to represent a gas molecule, right? A single one, not the whole number of particles, just a single particle. And remember that capital N, what that capital N stands for is the number of particles or the number of molecules that we have inside our gas, right? It represents the whole collective sample. So we need to be able to derive this equation. So how to derive the equation is you just draw a box first. Okay, so we're just going to imagine that we've got a box that contains our gas. Okay, we're going to imagine it's a cube box, so all lengths are the exact same, right? Length times breadth times height. It's going to be a cube box with sides of L. You're going to imagine that you've got your particle inside it. Okay, so let's just say it's a point particle. It's some mass m. We know that point particle with some mass m. Let's say it's moving with some velocity v in that direction towards the right. So we know what's going to happen is this particle is going to move the whole way to this wall and it's going to collide with this wall. Okay, so it's going to collide with this face of our container. That's what we're looking at. And we know that when it collides with that face of container, it's going to put a force on that wall of the container. Because in Newton's third law, when the particle puts a force on the wall of the container is going to put an equal but opposite force on our particle, which means it's going to move back in the opposite direction. So again, our particle is moving in the opposite direction. So if I took velocity to the right as positive, now if it's moving towards the left, it's going to have a mass, but its velocity is in the negative direction. So what I can do is I can write what is its change in its momentum. Okay, so the final momentum minus the initial momentum is my change. The final momentum is mass times velocity, is minus mv, right? Because it's going towards the left, the opposite direction. Take away the initial velocity, which was m times v. So that's my change in momentum. So clearly my change in momentum is going to be minus 2 mv. So that's what my change in momentum is. Another thing we know is that change in momentum can be used to represent impulse. So we know force is equal to the change in momentum over time, or we know force is equal to impulse divided by time. So I can write now is force is equal to my change momentum minus 2 mv divided by the time. Okay, so what I want to see now is the time. Time represents the time between collisions. So what we're going to imagine now is our particle, let's say it's just hit the wall. So it's hit the wall. What it's going to do is it's going to travel the whole way to the other wall. It's going to hit that wall, rebound, and travel the whole way to this wall again. So we can see that the time between collisions with this wall, remember that's what we're modeling is this wall. The time between collisions, we can write speed is equal to distance divided by time. So the speed that it was traveling at was our v. The distance it travels is it goes the whole way to this wall and the whole way back again. So it actually travels 2 times L divided by the time. So what we're representing here, that's the time between the collisions to hit that wall and come back in. The time between collisions with this wall. So what I can write now is my force is going to equal minus 2 mv divided by the time. And if I want to rearrange and see what time is, I can see time is 2L over v. So I want to divide by time, I want to divide by this, I'm dividing by 2L over v. And we know that in physics or maths, when you divide, it's seen by multiplying by the flip of the fraction. I got minus 2 mv multiplied by my v over 2L. So now you can see what's going to happen is my 2's are cancel, and I can write the force is equal to minus mv squared over L. Okay, so now what I would recommend doing is looking at your equation and looking at this equation and see how are they different. What I have here is a volume, but here I just have a length. So I'm thinking, how can I get from a force into a pressure and get a length into a volume? And what I know now is that pressure is always equal to force divided by the area, right? Pressure is force per unit area. So how I can write force is a pressure times by an area. So what I have now is there's my force. So if I want to get it into my force into a pressure, I have to divide it by an area. Okay, so maybe that's a better way to imagine it. So if I want to get a pressure, I need to take my force and divide it by an area. Take my force, which is minus mv squared over length. We've divided it by an area. So the area of that face is my L squared. We're dividing it by an area. So what I have now is pressure. Remember, dividing the same as multiplying by 1 over the fraction. So minus mv squared over L cubed. And another way of writing a length cubed represents my volume. So that now is my volume. So what I have now is I can just change that to say pressure times by the volume is equal to minus mv squared. Okay, so far that's pretty good. Pressure times volume, I've got an m, I've got some type of speed squared. But what I have here is a capital N, a third, and CRMS squared. So how do we relate those? So you have to remember what we did here is we modeled this for one single particle moving in one dimension, moving in our x dimension. But you know there's not one particle inside this box. There's going to be n number of particles inside this box. So I need to model it for n particles inside my box, right? There's not one, there's n. N is the number of particles that this box contains. So to find what pressure times volume is, it's actually negative n mv squared, right? So it's multiplied by the number of particles in the box. However, not all particles are moving in that dimension that we modeled. They're not all moving in that x dimension. We know that particles can move in the x dimension, they can move in the y dimension, and they can move in the z dimension. So that's why we use CRMS squared, the root mean square speed. Because if we can square all the speeds, so if I take all my speeds in the x directions, and I add it all to my speeds in the y directions, and add to my speeds in the z directions, we can take the mean of those, and that's going to become my c squared, right? So what we're doing is we're root mean square speed. What we did is we squared all the speeds, and we can use that that's going to represent c squared. So again, because we don't have particles just moving the x dimension, we have in the y and the z direction. So c squared is just taking account that they're moving in all dimensions, okay? But again, our equation models it for one dimension. So let's say we've got a massive amount of particles that say n is really large. What we can just basically say is all the speeds, basically in all the directions, are the same. So what I can write now is basically that 3 times x squared is equal to c squared. So maybe x squared is now equal to z squared over 3. So do you see that? And my x was my x direction that we represented with phi. So instead of writing v squared, I'm going to change it to c squared over 3. So I've got now is pv equals negative m c squared over 3. And you can see now that's what I have, 1/3 of nm CRMS squared. And you just get the right end of the negative because, again, the negative just is our direction because we modeled the positive direction in towards the right and the negative direction towards the left. So that's why you can just get rid of that negative then because it was only to count into our directions. Okay, something else you might be asking about is what even is the root mean square speed and why do we use it, right? Why do we take the squares of all the speeds? Okay, the reason why we take the square of all the speeds is because, again, remember, they're moving in all dimensions. So let's say I have a velocity of one particle moving at 5 meters per second towards the right. I have another particle moving at negative 5 meters per second towards the left. If I took the average of those, I'm going to end up with 0, right? To the average, add them together and divide by 2, I'm going to end up with 0, right? Because 5 plus minus 5 is 0. So you can see if we take the mean, we just take the mean, we end up with 0, right? Which doesn't make sense because the speed of the particles, the velocity of the particles should be representative. It's correlated to the kinetic energy of the sample, right? We can see that the mean of their speeds is correlated to their kinetic energy, right? So the kinetic energy can't be 0. So to account for all these negatives and positives, to account for all these directions, because remember velocity is a vector, that's why we square them all. Because if you square 5, you get 25. And if you square negative 5, you also get 25. So what we do is that's why we square all the speeds So we can actually see that the speeds represent or correlate to their kinetic energies. So that's what we do is we square them all. So root mean square speed, just means you square them all. Then you take the mean of that number. So let's say I had 3 numbers squared. I divide by 3, like we did here. And then we just take the square root of that number. So I just take the square root of that number at the end to finish with my final units of meters per second. So let's look at a question now. So, I just gave myself a shock. This question says, a balloon is a mixture of helium and argon atoms at this temperature. I want to calculate the root mean square speed of the argon atoms and compare their kinetic energies. And we're given the molar mass of the argon atoms. So I'm going to calculate the root mean square speed. So what I do to calculate the root mean square speed, I have these 2 equations. Okay, so to calculate the root mean square speed of our argon atoms, I can either use their pressure times their volume times 1/3 the number of particles we have times their mass. But I don't have pressure and volume anywhere here. So I probably wouldn't use this one. I would look at this equation. And I can see that the kinetic energy of a molecule is equal to this equation. So I do have the temperature, so it's nice this one. So what I'm going to do is to calculate the root mean square speed, I'm going to say that because we're looking at a kinetic energy of a single gas molecule, that 1/2 of the mass of the CRMS squared is equal to 3/2K times T. So that's what I have now. So pop in my numbers. I know that 1/2 of the mass times by CRMS all squared is equal to 3/2 times the Boltzmann constant, which is 1.38 times 10 to the negative 23, multiplied by the temperature, which was 310 Kelvin, because remember temperature has to be in Kelvin there. Okay, so what I'm trying to do is calculate what this root mean square speed is. So I'm trying to do that, I must know the mass from something else in the information. So again, we're trying to figure out what is the mass there. So what I'm told is the molar mass. So again, I'm told that 0.04 kilograms is the mass of 1 mole, right? That's what that means. Again, if it was 10 meters per second, you're traveling 10 meters per second or every second. So 0.04 kilograms per mole is that 1 mole is 0.04 kilograms. But I don't want the mass of 1 mole. What we're doing here, this equation, remember, is the mass of a single particle. So I don't want 1 mole, I want 1 particle. I need to know what the mass is of 1 particle. And I remember that 1 mole is what is the number of particles of Avogadro's constant. So 1 mole is equal to 6.02 times 10 to the power 23 particles. Remember, 1 mole is that Avogadro's constant. Avogadro's constant is just a way to quickly say that's the number of particles inside 1 mole. Okay? So inside 1 mole, there is that number of particles. So I don't want to know the mass of 6.02 times 10 to the power 23 particles. Again, I just want the mass of 1 particle. So you see on this side, we just divide it through by Avogadro's constant. So to get the mass of 1 particle, we're just going to divide through by Avogadro's constant. So go to 0.04, divide it by 6.02 times 10 to the power 23. And we get a number there of 6.64 times 10 to the negative 26 kilograms. So that's the mass of a single particle. So now what I can do is I can put my mass in here. So what I can do now is 1/2 times my mass, 6.64 times 10 to the negative 26, 6.64 times 10 to the negative 26, times by the CRMS squared is equal to 3/2 times my Boltzmann constant, 1.38 times 10 to the negative 23, times my temperature, which is 310 Kelvin. So now we can solve through for what CRMS is, my root mean square speed. So to find it, all I'm going to do is do my Boltzmann constant, 1.38 times 10 to the negative 23. We're multiplying by our temperature, which is 310. We're multiplying by 3, and then you're dividing that number by 2 to figure out here what was our kinetic energy of one of those particles. Then we have to divide through by that number. So what I'm going to do is I'm going to multiply by 2 first, and then divide by 6.64 times 10 to the negative 26. And remember, that's going to give me CRMS squared. So just to get CRMS, you take the square root of your answer. So we can write a CRMS is 439.64 meters per second. Okay, probably recommend you double check that one just because it's a lot to put in your calculator in one go. So again, what we did is 3/2. We multiplied by Boltzmann constant, 1.38 times 10 to the power of negative 23. We multiplied by our temperature to figure out what our kinetic energy was of a single particle. And just to make sure you're good, if you want to know what that number there is, the kinetic energy of one particle is 6.417 times 10 to the power of negative 21 joules. What we have to do then is we have to divide by a half times the mass to figure out what our CRMS squared is. So what we're going to do is divide by a half, the same as multiplying by 2. And we're divide by our 6.64 times 10 to the power of negative 26. And remember, that's going to give us squared, CRMS squared. So to get what CRMS is, the root means square speed. We have to take the square root of that answer, and we get 439.64 meters per second. So the very last bit then says that we need to compare the kinetic energy of the helium and the argon atoms. Okay, that's why I wrote what the kinetic energy was up here. Because see, the kinetic energy of a gas molecule is equal to 3/2 kT. Both of them are the exact same temperature. They're both at 310 Kelvin. K is a constant, so because both of them are the exact same temperature, they both have the same kinetic energy. So what we're saying is they have the same kinetic energy. Because again, the kinetic energy is related to their speeds, and we know their speeds are related to whatever temperature they're at. So, grand.